So now, let me give you an example. C 0, 1, I guess you read this is a set of continuous functions on the interval 0 to 1. Let's put C tilde 0, 1 as f is in, it has to be continuous on 0 to 1, but I'm going to add another requirement that f of 0 is same as f of 1. So things in this C tilde would be like there's some function that's like this, and these two values have to be the same. Or it might be so you have to have same values, right? Then take two functions from C tilde, right? And add the two. The question is, if you add one function like this, another function like this, add the two, will the sum still be continuous? Yeah, if you have a connected graph, another connected graph, if you add them, you'll still have a connected graph, right? Would the endpoints have the same value? Well, if let's say this is like 2 and let's say this is like 3, then the f plus g would have 5 on both sides, right? So this will still be in C tilde, right? And you know, addition is commutative. Addition of two functions, I mean, this should be obvious. Like 0 itself will be in C tilde, right? 0 has endpoint values the same. It's connected, it's continuous. Okay. What about negative? Well, if you have f, negative f is also in C tilde, right? And if you add them up, you get 0. So these 4 items will be true. Can you also multiply any constant C to f? What would it do if I multiply by 2? It will just make it lengthen twice, but it will still be continuous and the endpoint values would be true. The endpoint values will match. It will still be true.
So if you would change the period, that's when it would be under C tilde, right?
Yeah, so if you have f cx, this wouldn't be in C tilde.
Gotcha.
Yeah, but then we don't care because we already have, one claim is that this can act as a scalar multiplication, right? It will satisfy both conditions, right? And it will also satisfy these as well. So now you have a vector space C tilde. Well, you can also convince yourself that there's nothing special about 0 and 1. You could put these two numbers as anything you want, right? So what if I put something like negative pi to pi? That will still be a vector space. The same kind of reasoning will hold, right? Agreed? Right. So what? Well, it's nice that we have a vector space. Does this give us anything? Well, this is when we think about other things that we were able to do in the usual vector spaces. So I talked about the fact that if you have a three-dimensional space, you can choose any three vectors in different directions, right? To represent any point in 3D. You can make any point as a linear combination of these three vectors. Isn't it right? So the next question is like, what is the dimension of this vector space? That would be like one thing that you might ask, right? but it's really, this is huge, right? You can draw any kind of vectors and any kind of function, and there will be a vector in this vector space, right? But here's something that we also know. If you have any function that's periodic from negative pi to pi, we can say that that function f of x is equal to a0 over 2 plus summation n from 1 through infinity an cosine nx plus bn sine nx. What is this thing called? The Fourier series, right? It's called the Fourier series. And look at each of these elements. This is a constant that belongs to this space, right? Cosine, it's a periodic function that's from negative pi to pi. Cosine is like that, right? Depending on how many n's that you have. If n is 1, it's what is it? It's like that's when n is 1, right? But then if n is 2, you have some more of this, right? So if n is 2, you have some more, but it still belongs to C tilde, right? This one also belongs to C tilde for the same reason, right? And what did you do here? You've made any periodic function from negative pi to pi that's continuous as infinite sums of elements in that space. So you can think of this as 1 here. 1 cosine nx and sine nx. So it's like sine x, sine, cosine x, sine x, cosine 2x, sine 2x, and then on and on and on, right? This thing forms, what is this thing called again? Basis for C tilde, yeah. A set of basis vectors. This gives you basis vectors for C tilde. Okay. So,
And that could be any vector, right? That's what that means, the basis vector?
right. So, okay. So that's another important thing. See, I chose this as a basis set, but basis is not unique, right? You can very well come up with different kinds of bases if you want, right? So you know this better than the other kinds because we use this to solve PDEs in differential equations, right?
Can basis vectors also be unit vectors?
Basis unit vector? Oh, yeah. So, okay, so the thing is, what's a unit vector? Unit vector is size 1, right?
Right.
But to have size 1, you need a norm. Norm is defined as an inner product. So if you have two vectors u dot v, right, then the norm squared is same as v dot v, so that the norm can be defined as the square root of v dot v. And that says that in order to have a norm, to have a unit vector, you need a norm, because you have to divide by the norm to normalize a vector, right? But then to have a norm, you need a dot product, or an inner product, that's another name for it. So you might think of what's like the appropriate dot product in this space. And we say that if you have one function and another function in this space, in general, we don't put dot, rather we use inner product is like that, but it's like inner dot product, okay? So how do we define dot products for vectors? We do component-wise multiplication, we add, right? But the thing is, this function has all kinds of different values for each x. So we have to multiply those two values, right? But then all of these has to be summed up. How do you add infinitely many things that's continuous? Well, you integrate, right? And that would act like a dot product. You can define the unit. And if you do that, then you can see that the normalized ones are 1 divided by square root of 2 pi. And cosine nx should be divided by square root of pi. Sine nx has to be divided by square root of pi as well. And that gives you a very nice way of finding the coefficients. So if you know that, then we see. If you instead put those numbers there, so these are unit vectors, then I'll just put A0. Okay. So if you write it like that, then you can just say that A0 is simply the function multiplied against this thing. From negative pi to pi. Because, this is like, finding this value is like projecting this onto this unit vector. And, projection of a vector over a unit vector u is simply v dot u, right? So all you have to do is you have to do the inner product with this, you get A0. And an would be what? From negative pi to pi of f of x times cosine nx divided by square root of pi dx. If you do that, you basically recover all the formulas of the Fourier series. So you actually see that what we learned as the Fourier series in differential equations is really linear algebra. Another question, what's the dimension of this space? Size of the basis vectors, how many do we have? Infinitely many. So what's the dimension of this vector space? Infinite dimensional. So once you know enough abstract vector space, then you can basically deduce the Fourier series that way. That's a cool thing, right? That's why linear algebra is so powerful. You can even cover Fourier series.